Section 3.5 is on page 113, talks about non-homogeneous equations, method of undetermined coefficients. Okay, there are 3 ways of solving those. We're going to learn 2 of them. Let y double prime plus pt of y prime plus q2 of y plus g of t, where p, q, g are continuous functions on open interval. The same traditional linear differential equation, in this case in second order. The general solution of the non-homogeneous equation. So notice here, this is not equal to 0, and that's why it is non-homogeneous. The solution here, the general solution, is of the form y equal, they call this, the book calls it the complementary solution. I'd like to call it the homogeneous solution, plus the particular solution. The particular corresponds to g of t. And the homogeneous we already did. We did that in section 3.1, 3.3, and 3.4. So that doesn't change. Where y1 and y2 form a fundamental set of the solutions corresponding to the homogeneous equation, C1 and C2 are arbitrary, and y sub p is any solution of the non-homogeneous equation. So, we're going to focus on 3 types of non-homogeneous problems. Now, of course, g of t, when I say g of t, I'm referring to this. G of t could be anything. We're going to focus in these sections on specifically an exponential, sine or cosine, not trig, specifically sine or cosine, or a if I see that the right side consists of a e to the rt, then I let the particular solution be the general case, a e to the rt. If I see on the right hand side a sine or a cosine, I let the particular be the cosine and the sine combined, matching the angle. And if I see a polynomial of degree n, you make sure that you list the entire general polynomial. So if this is 3t squared, for example, I would say at squared plus bt plus c. Find a, b, and c. So let's start. I'm glancing at problem number 2. This is on page 141. So it's very close to what we did. I'm looking at this. It says, find the general solution of the differential equation. Well, let's start. If I look at this problem and say, all right, I happen to see a second order linear differential equation for the homogeneous part, which is the complementary part. So instead of homogeneous, not this book, all books refer to it as the complementary part. I'd say let that equal e to the rt, y prime will be r e to the rt, and y double prime will equal r squared e to the rt. So this is pretty much section 3.1, 3.3, and 3.4. That's not going to change. E to the rt times r squared minus r minus 2 equals 0. E to the rt cannot equal 0. And r minus 2, r plus 1 equals 0. R equals 2, r negative 1. So here we know that the complementary part, so we know that y equal the complementary plus the particular. Complementary I already found. It is C1 e to the 2t. Maybe I should list the fundamental set. Plus C2 e to the negative t. So that's done. That's what we did before. The added part now is this particular solution. We look at this and we notice this is a polynomial. We say let y equal second degree at squared plus bt. You know what? I'm going to shift this to the right a bit. Plus c. So I need to satisfy this equation. I need 2 derivatives of that. y prime is 2a t plus b, y double prime is 2a, and if I plug those in, this says 2a minus 2at minus b minus 2 times, and I'm going to shift this even more, nice, 2 times, that's negative 2at squared minus 2bt minus 2c. So basically, it is 2a minus 2at plus b minus 2 times at squared plus bt plus c. And that right there will give me, if I look at the t squared, negative 2at squared. If I look at the t, that should give me plus a negative 2a minus 2b t plus the terms without a variable, that will be 2a minus 2b minus 2c. Now, that must equal this. All of that, it must satisfy the equation. That must equal negative 2t plus 4t squared. And this is how I work it. I take the quantity in front of the t squared and say that must equal to the number in front of the t squared, which means a is negative 2. And I'll take the quantity in front of t, and it must equal the quantity in front of t. Negative 2a minus 2b equal negative 2. But I know a equal negative 2, so that is 4 minus 2b equal negative 2. That means 6 equals 2b, and b would be 3. Got it? So I got this to be a negative 2. I got this to be a 3. And if I take the constant term, and since there's nothing there, that must equal 0. Twice a, but I know a is negative 2. Minus 2b, but I know b is 3. Minus 2c must equal a 0. So this will yield, let's see how that works. Let me get rid of this. That would yield negative 4 minus 6 minus 2c equals 0. That's a 10, negative 10. So that would mean negative 2c equal a 10. c equals a negative 5. So my solution here would be, if I really look at the whole thing, y would equal c1 e to the 2t plus c2 e to the negative t plus the homogeneous, the non-homogeneous, that would be a 2t squared plus 3t minus a 5. So anytime they say find the general solution, homogeneous, you could leave c1, c2 like we did back in 3.1, 3.3, and 3.5, but the particular, you always find those coefficients. Okay, one tiny exception. That right there should have been a negative b. That means the last step, that should have been a negative 3. That makes that a negative 7. So that makes this negative 2c equal 7, or c equal negative 7 halves. That happens a lot. And there it is. Now the following example, I wanted to do it as a warning for you guys, the order you should do this in. You are looking for y equal the complementary part, which is the homogeneous, and the particular part, which is the new stuff. If you start with the particular part, you could end up messing up on few things. That is, if you start with let y equal a e to the negative t, I need two derivatives. Y prime is negative a e to the negative t, and y double prime is a e to the negative t. If I plug those in, y double prime plus 3 times negative a e to the negative t plus 2 times a e to the negative t. That should equal 3e to the negative t. That's how I solve for a. If I combine those, a plus 2a, that's 3a, minus 3a, that's 0, equal 3e to the negative t. We have a problem. Why is that? This can never happen. So if I start with that particular solution, this could happen. Why is that? Because if I look at the complementary, if I look at the homogeneous section 3.1, 3.3, and 3.4, this deals with the traditional, let y equal e to the rt, y prime equal r e to the rt, y double prime equal r squared e to the rt, r squared e to the rt, plus 3r e to the rt plus 2e to the rt equals 0. Factor e to the rt out, you have r squared plus 3r plus 2 equals 0. E to the rt can never equal 0. So it must be r plus 2 into r plus 1 equaling 0. That means r is negative 2 and a negative 1. And e to the negative 2t and e to the negative t. So I could say this is actually c1 e to the negative 2t plus c2 e to the negative t. And let's see how much did we learn from linear algebra. Do we see that when we let y equal a e to the negative t, that's a linear combination of this? And from this, I know those two come from the homogeneous. What does that mean? That means if I take any multiple of this and plug it in, I'm going to get a 0, which is exactly what happened. So this happened to be one of the homogeneous solutions. That's why it will never work. So it turns out it's very important you start with finding the complementary first, and then you proceed and find the particular. Why is that? Because once you decide on this, you would know that, you know what, something went wrong. Well, something's gonna go wrong for sure. And if you recall, how could we take this and make it linearly independent from this? Do you remember? You let y equal a, you multiply it by t. Do you recall that? And now you say, let's take y prime. That is a e to the negative t minus a t e to the negative t. Y double prime, negative a e to the negative t minus a times the product rule. Derivative of the first times the second, plus the first times derivative of the second. So if I take y double prime right there, I'll get negative a e to the negative t minus a e to the negative t plus a t e to the negative t plus 3y prime plus 3a e to the negative t minus 3a t e to the negative t plus 2 times, and that must equal 3e to the negative t. So those are alike. I start with the t first. If I look at the terms with a t, at, that's 1 plus 2, that's 3 minus 3, they cancel out. But I'll notice this is negative 2a e to the negative t plus 3. That will make it 1a e to the negative t. You could factor e to the negative t out of those, and that will save the day. And what does that mean? That means a must be 3. So the solution here is that plus 3t e to the negative t. So there's no way of knowing whether I need to modify this or not unless I find the complementary first. If this happened to be either of those, I need to modify it by multiplying it by t. And that's the only way that will work.